Hello everyone. Have you ever wondered why metal utensils heat up faster than water, even when both are on the same stove? That difference comes down to something called specific heat capacity. It's basically a measure of how much energy a substance needs to raise its temperature. If it needs a lot of energy, it heats slowly. If it needs little, it heats fast. Now, in gases, we deal with two types of specific heat, one when the gas is heated at constant volume and another when it's heated at constant pressure. At constant volume, all the heat goes into increasing the internal energy, but at constant pressure, part of it is also used to expand the gas. That's why Cp is always greater than Cv. And for all ideal gases, the difference between Cp and Cv is a constant, R, the universal gas constant. That's 8.314 joules per mole per Kelvin. Pretty elegant, right? Let's start simple. Monatomic gases like helium or argon. These are the minimalists of the molecular world. They can only move in three directions, x, y, and z. So, their energy comes purely from translational motion. The total internal energy per mole is 3 by 2 RT. That means the specific heat at constant volume, Cv, equals 3 by 2 R. At constant pressure, Cp equals 5 by 2 R. And when we take their ratio, gamma, or Cp by Cv, we get 5 by 3, which is about 1.67. So, monatomic gases heat up quickly because they've got fewer ways to store energy, no rotation, no vibration, just pure straight-line motion. Now let's step it up. Diatomic gases like oxygen and nitrogen. They have two atoms, so besides moving, they can spin. They've got extra ways to hold energy. In total, they have 5 degrees of freedom, 3 for movement and 2 for rotation. So, their internal energy per mole becomes 5 by 2 RT. Their Cv is 5 by 2 R and Cp is 7 by 2 R. That gives a gamma of 7 by 5 or 1.4, a number you'll often see in aerodynamics and sound calculations. That's why air, mostly nitrogen and oxygen, behaves like a diatomic gas with gamma equal to 1.4. Now, what happens if we keep heating our diatomic gas? Well, the molecules start vibrating. These vibrations add two more energy terms, kinetic and potential, which together contribute an extra RT per mole. So now, total energy becomes 7 by 2 RT, Cv becomes 7 by 2 R, Cp becomes 9 by 2 R, and gamma drops to 9 by 7, roughly 1.29. So the more the molecules vibrate, the more heat they can absorb without their temperature rising much. It's like giving them more pockets to store energy. Let's talk about the overachievers, polyatomic gases like carbon dioxide or methane. These molecules don't just move and rotate, they also vibrate in multiple directions. They have 3 translational degrees of freedom, 3 rotational ones, and several vibrational modes. Let's call that number F. So, the total energy per mole becomes open bracket 3 by 2 plus 3 by 2 plus F close bracket RT. That means the specific heat at constant volume, Cv, equals open bracket 3 plus F close bracket R. And the specific heat at constant pressure, Cp, equals open bracket 4 plus F close bracket R. The ratio of the two, gamma, equals open bracket 4 plus F close bracket divided by open bracket 3 plus F close bracket. So, as the molecular structure becomes more complex, energy spreads into more modes of motion, which means the gas's temperature increases more slowly for the same amount of heat added. Pretty fascinating, right? The more ways a molecule can move, the more ways it can store energy. Let's try a quick example. Suppose a gas has Cv equal to 20.8 joules per mole per Kelvin. We know that Cp minus Cv equals R, or 8.31 joules per mole per Kelvin. So, Cp equals 20.8 plus 8.31, that's 29.11 joules per mole per Kelvin. Now, divide Cp by Cv. 29.11 divided by 20.8 equals 1.4. That's our gamma, the same as air's. So yes, air behaves like a diatomic gas under normal conditions. Now, how does all this tie into the law of equipartition of energy? It says every degree of freedom gets an equal share of energy, half kT per molecule. So, if a molecule has F degrees of freedom, the total energy per molecule is F by 2 kT for 1 mole, multiply by Avogadro's number, and we get U equals F by 2 RT. That's why Cv equals F by 2 R and Cp equals F plus 2 by 2R. And that's the secret. Heat capacity depends entirely on how many ways the molecule can move, spin, and vibrate. Let's wrap it up. Specific heat capacity tells us how much energy a gas can store. Monatomic gases only translate, so they heat up fast. Diatomic ones rotate too, so they absorb more heat. And polyatomic molecules? They're energy sponges. No matter the gas, Cp minus Cv equals R always. And remember, as molecules get more complex, gamma, the Cp to Cv ratio, drops because energy spreads out across more degrees of freedom. So next time you feel hot air from a heater and cool air from a can of compressed gas, remember, it's the same principle of energy sharing and molecular motion in action. Alright everyone, that's a wrap for today's concept. I hope now you understand how gases store and share energy in different ways. See you next time with another fascinating journey into the microscopic world of physics.